Hello everyone, this is Dr. Young, and in this video we're going to talk about the standard heat of formation. So we'll talk about what these heat of formation equations look like, we'll talk about the fact that we have just tables and tables and tables of this data, and we'll hint at how we can use these to figure out the heat of reaction for reactions that we can't do calorimetry on. So to start off, right, heat of a reaction, we sort of touched on this a little bit with the calorimetry stuff. But the heat of the reaction is just, it's like the enthalpy of the reaction. It's the change in the energy when a reaction occurs, right? When you're making and breaking bonds, things are either going to require energy or release energy, right? They'll be either exothermic or endothermic. And if you remember, right, you look at these energy diagrams here, this is supposed to be energy, or you could say it's enthalpy. We'll talk more about later how there's also entropy and everything, but let's not go there yet. And so in this first graph, right, you start up high, you end up dropping in energy, so your delta H or your delta E, right, your change in energy is going to be negative. You're going to go down in energy. You have an exothermic reaction. And the one on the right, again, increasing in energy. In this one, you are starting at a low energy, and you're going to go up to a higher energy. So now your delta H is some positive value, and you've absorbed energy, which makes it endothermic. And every reaction has some sort of heat of reaction, some sort of, did they go up in energy, down in energy, or some have zero, right? Some have zero. Yeah, that's a legit number too. And so here I have an example of the formation of ammonia, right? Where you take 3 moles of hydrogen, 1 mole of nitrogen, and that makes 2 moles of ammonia, of this NH3. And it looks like apparently for this one, right, your delta H of reaction is negative 92.2 kilojoules per mole. All I really care about here is that I see that the delta H is negative, which means that this is an exothermic reaction and that its energy diagram is a downhill energy diagram. So it looks like it's exothermic. Now the question is, how did we find this out? Like, how do we know that the delta H, that the heat of the reaction for the formation of ammonia is negative 92.2? Well, let's talk about that. One way is what we are talking about before, which would be calorimetry, right? Remember in the previous video, we talked about how you could take a calorimeter, right? So you've got your, styrofoam type cup or whatever it is. You stick a thermometer in it, right? It's going to have some sort of temperature. You fill it up with water of a known amount, and then you have a little chamber in here in which you do some sort of reaction, right? You do some sort of reaction, it goes poof, and then the idea is that it released heat from the reaction into your water, or vice versa, or it absorbed heat from the water into the reaction. And we could measure that by measuring what the change in the temperature was of the water, right? So you could tell by the change in the temperature of the water how much heat was transferred, and therefore how much heat was transferred because of the reaction, right? We said Q of the reaction was equal and opposite to the Q of the water. I'm not going to do this calculation again. You can go back and look at the previous video for how we did this. But this process is not always possible for a given reaction, right? And that's what I'm saying down here. It's just not always possible. Sometimes as soon as you mix two things, they start reacting. Sometimes you need special conditions to get them to go. These reactions work well if you can just like add a little spark, like stick a wire in here and add a little spark, and all of a sudden the reaction goes, like combustions. But it's not always feasible. So what else can we do? What we can do instead is that we can use the heat of formation, or the enthalpy of formation, right? So this delta H naught F. What we can use is this heat of formation to figure out what the change in the energy would be for a reaction. So let me talk to you first about what the enthalpy of formation, what the heat of formation is. So we're talking about the standard heat of formation here, right? Where we have that delta H with the naught, that's that little degree symbol, F sub F. And so the enthalpy, or in other words, the change in energy or the heat, that heat change is coming from when you form 1 mole of the substance at the standard state conditions from pure elements. So, right, so you're making 1 mole of the stuff, standard state conditions, pure elements. Now, standard state sounds a lot like STP. This is different, right? This is not STP, which is standard temperature and pressure. It is similar to STP in that the pressure at standard state is 1 atmosphere, like it is for STP. In fact, let me just write out what it is for STP, right? Remember that STP is 1 atmosphere for the pressure. That's the standard pressure. But their standard temperature is 0 degrees Celsius for STP. For standard state, it's 25 degrees So it's like quote unquote room temperature, but it's actually a little higher than most room temperatures, at least in the States. And standard state also says that all solutions are of 1 molar concentration. And the idea behind a standard state is just so that you can compare reactions across a wide variety of conditions. You just put them all in the same conditions so you can compare, like, oh, look, this one releases more energy than that one. This one has a larger change in entropy than that one. And so we have this standard state, and it's just to kind of standardize reactions. There's no real like physical reason why we're using it. It's just to standardize stuff so that we can make comparisons between two different things. And so this is just for, this heat of formation stuff is just for compounds, not pure elements. So if I'm looking at bromine, right, the example for bromine, we're talking about making 1 mole of the thing, and bromine is just Br2, and it's a standard state, so bromine is a liquid, right? It's a liquid at 25 degrees Celsius, which is why I put the liquid symbol there. But bromine, we're saying that you make these things from the pure elements, right? From the pure elements. Well, bromine is already a pure element, so this doesn't really make sense. This is not really a thing. So what would it take to make this? It would take no energy. Kilojoules per mole. It takes no energy. Because we're saying that the heat of formation of a pure element from a pure element doesn't take any energy. We're just going to say all pure elements, their heat of formation is zero. Where we do use this is for things like carbon dioxide. What we're saying is that for carbon dioxide, right, so CO2, I'm going to take 1 mole of it. Now, what was it made from? It was made from carbon, and it was made from oxygen. But now these are coming from the pure elements. Carbon as a pure element is just carbon. That's great. But oxygen as a pure element is actually a diatomic element, so it's O2. So my reaction here, right, my heat of formation reaction would be 1 carbon plus 1 O2 molecule makes 1 CO2. And you can look this value up. I'll show you a table in a little bit, but you can look this value up and see that, oh, apparently to do this, that releases 393.5 kilojoules per mole. And these are just values that you can look up at NIST or in a textbook. Sodium chloride, similar idea. Again, 1 mole of sodium chloride, so NaCl, and it would be solid at room temperature. It's made from sodium, the element, and then chlorine is an element too. It's Cl2, it's a diatomic element. But this is not balanced, right? We have to make sure that all these were balanced. For the carbon dioxide, that was fine, right? 1 carbon, 1 carbon. 2 oxygens, 2 oxygens. But right now, I'm not balanced, right? I have 1 sodium on the left, 1 sodium on the right, but I have 2 chlorines on the left and 2 chlorines on the right. Now, what makes this kind of different than normal balancing, a normal balancing of an equation, is that you only make 1 mole of the substance, right? So I can't change the stoichiometry in front of the product. I'm not going to change the stoichiometry in front of the NaCl. It's always just one of these. It's always just 1 CO2, 1 bromine, 1 magnesium sulfate, which we'll see in a second. It's always just 1. So what that means is I might have some funny looking coefficients like 1/4, 1/8, 1/2. So if I want 1 chlorine, from Cl2, really I'm saying is I just want 1/2 of these. I just want a half of a Cl2 molecule. And that's how you're going to see these equations written. This would be 1 Na plus a half of a Cl2 makes 1 NaCl. And again, you're going to be able to look up values like that. This one would be negative 411 kilojoules per mole. And there's no way to look at this and be like, well, it looks like it'd be positive or negative or anything like that. These are just things you'll look up. And let's do magnesium sulfate too. So MgSO4. Magnesium sulfate looks like it's made out of magnesium. It's made out of sulfur. And it's made out of oxygen. Now, we already talked about, we know that oxygen is O2, so check. I got that. Let me give myself a little more space. I know that oxygen is O2. Magnesium, Mg. Magnesium is just monoatomic. Sulfur is a weird one, though, and I'm trying to put in the weird ones so that you see them. Sulfur is S8. Elemental sulfur is usually an S8 allotrope. So it comes in eighths, which means we're going to have to use some weird coefficients for that. I don't want, right? I do want one magnesium, check. One magnesium here, I'm good. But I only want one sulfur in my magnesium sulfate. I don't want 8 sulfurs. So what I have to do is I have to put the coefficient in of 1/8 of an S8. I want 1/8 of an S8. I don't want a whole one. I just want 1/8 of it. I just want one sulfur atom. And then for my O2s, right, I have O2s. I want 4 altogether. I want 4 oxygens altogether. So I need 2 of the O2s to get all of my oxygens that I need for the magnesium sulfate. And again, you could look up this value. I won't put it on here, but you can look up this value. It's negative 1200 and something. But that has a value, right? So the point of these is that I want you to pay attention to the fact that we made just 1 mole of these, right? There's only 1 mole of CO2, 1 mole of NaCl, 1 mole of magnesium sulfate. And they all came from pure elements, right? That we're saying that this, if you take just the pure elements and you add them together, you're going to get this compound. So, you're going to have to deal with things like O2 or S8 or Cl2 or stuff like that. So I want you to practice this now. Let's take a look. Oh, actually, let me show you a table of. So here's a table of the heats of formation. This is just a tiny table that I found somewhere on the internet. If you really want to find good tables, NIST is the place to go. So here's a web page where you can look it up by formula, which is the National Institute of Standards and Technology. But you can go to this form. You can find out any heat of formation of any compound that we know, and you can see that they just list them, right? You have the compound in the phase, and then the heat of formation for all of these different compounds. I mean, we just know so many. Your book has a appendix full of them. You'll see examples used in the textbook chapters itself, or you can just look them up if you need them to figure out some homework problem or some lab problem. You can use them. Now, what I want you to do is to pause and take a moment here and write the formation reactions like I did 2 slides ago for silver 1 bromide, ethane, acetone, and phosphoric acid. So I want to see what elements you need to combine to make this compound. So go ahead and pause and see what you can do. Okay, so hopefully you took a moment there, right? So we have silver bromide. So I just write the formula. I know it's silver 1 bromide. And then I need to look at, well, what's in it. I've got silver in it, and I've got bromine in it. And I know bromine is one of the diatomic elements. Remember your Brinkelhoffs or your Have No Fear of Ice Cold Beer. So I got Br2. Is this balanced? No, it's not balanced. I have too many bromines over here on the left-hand side. I don't want 2 bromines. I just want 1 bromine. So I need to put a 1/2 in front there. I just want a 1/2 of a Br2. And now that's all nicely balanced. And then I know the delta H heat of formation, right? The heat of formation here apparently is negative 99.5 kilojoules per mole. If I do the same thing, and that was just on this, I took a little clip out of this table so you could look that up and see it yourself. Same thing for ethane. If I try to do ethane, so we got C2H6. Ethane's a gas. You don't really probably know that, but that's okay. It doesn't really matter too much at this point. But it came from carbon, which is monoatomic, and it came from hydrogen, which is diatomic. Carbons, how many carbons do I need? I need 2. How many hydrogens do I need? I need 6 altogether, so I need 3 of the H2s. And I could go over to my little table here and see, oh, look, here is that propane, or that ethane, excuse me. And its delta H is negative 84.7. And you'll notice, by the way, that some of these values are positive. Not all of them are negative. There are some positive values too. That's totally fine. You just will always report that sign. And to kind of give you a preview, I'm interrupting myself already, but to kind of give you a preview of why we're doing this is we're going to be able to use these heats of formation to then deduce what the heat of a reaction might be that involves these compounds. Like if you know how much energy is sort of embedded in these compounds, you can then do some math to figure out what that change in energy would be if these compounds changed. And so that'll be in the following video. But let's finish acetone and phosphoric acid here. Acetone, C3H6O. I've got carbon, and I've got hydrogen, and I've got oxygen. Got to make it all balance out. So I need 3 carbons. I need 3 H2s to get my 6, but I need 1/2 of an oxygen to get just that 1 O. The delta H formation is not on here, but you can just look it up and you see that it's negative 249.4 kilojoules per mole. And then phosphoric acid, same deal, H3PO4. Now this one's kind of tricky, and that's why I wanted to include it in this video. And I got my phosphorus, and I've got my oxygen. It's kind of tricky because phosphorus is another weird one. So sulfur and phosphorus are really the 2 weird ones. Aside from the diatomic elements, sulfur is always S8, and phosphorus is always going to be P4. So P4, S8. Those are going to be 2 that you want to know for these types of problems. And then I just got to make sure things balance out. I only want 3 hydrogens, not 2, so I want 3 halves of an H2. I only want 1/4 of this P4, and I want 2 of these O2s. And then again, you can just go look up these values. I'll put this one here. Delta H of formation is negative 1,288-ish kilojoules per mole. So like I said, you want to be able to draw these equations. You want to know where these delta heats of formation come from, right? This is the amount of energy that's released or required to make these compounds from pure elements. But we're going to use these to deduce what the heat of a reaction is in cases where we can't use calorimetry. So that's what's going to be in the next video. So practice a couple more of these. Keep studying. Good luck.